Welcome to Global Virtual School students. This is your chemistry first year class. I'm Dr. Ijaz Bano and we are on chapter number 2, atomic structure, and the topic for today's discussion is derivation of energy, frequency and wave number of orbit. And in previous lecture that was also about the Bohr atomic model and its application. In that we calculated the radius of the nth orbit of hydrogen atom, and this lecture is the continuity of the previous topic, that is Bohr's atomic model. Students, after completing this topic, today's topic, derivation of energy, frequency and wave number of orbits, you will be able to use Bohr's model for calculating energy, frequency, wave number, and you will also be able to relate energy equation to frequency, wavelength and wave number of the radiation emitted or absorbed by electron by different expressions, or you can say the equations. I will just recall you that in previous lecture we have calculated, Neil Bohr actually calculated, he derived the expression or formula or equation to calculate the radius of the nth orbit, and its equation is r equals to n square h square epsilon z pi m e square. And in this formula, n square and atomic number z is variable while all other are constants, and putting the constant values we got 0.529 angstrom, and in that way you can calculate the radius of any orbit, first, second, third, fourth and so on. Now is the derivation of energy of an orbit. For an student, you know energy of any system, and in this case energy of an electron in an orbit is the sum, addition of the potential energy and kinetic energy. And you know potential energy is due to its position and kinetic energy is due to movement of the electron, and kinetic energy is half mv square. M is the mass of electron, v is the velocity, and potential energy is minus ze square divided by 4 pi epsilon r, and z is the atomic number of atom, e charge on electron, pi is constant, epsilon is again constant, and r is the radius. And this is in negative because when electron, this is very important to understand, when electron is out of influence, out of attraction of the nucleus, then it has zero energy. As it brings at a distance r from the nucleus, and it is under the influence of nucleus, its energy reduces from 0 to towards minus, because extra energy emitted, and it is under the force of attraction, and it is going to be stabilized, and because energy is released and its energy reduces from 0 towards minus value. So this potential energy is in negative for electron, and their sum is like kinetic energy plus potential energy. Just keep the values of kinetic energy plus potential energy. This one is negative for with potential energy equation. So, and you know when positive and negative multiply, there is a negative always. So this equation, like kinetic energy plus potential energy, we have this equation. Students, if you remember in from previous lecture, while we were calculating the radius of an electron, there was a factor mv square, and this mv square was equal to ze square divided by 4 pi epsilon r. I can show you this from that slide, like this one. This was z square, 4 pi coulomb's force and centrifugal force, and when these factors were cancelled, then there was this mv square equals to z square divided by 4 pi epsilon. So putting this value mv square, in this case this one mv square, keeping this value here, we got this equation 1 by 2, and this ze square 4 pi epsilon r minus ze square divided by 4 pi epsilon r. So from these two sides, take out the common factors out. Which are the common? So these are the common, z square over 4 pi epsilon r, and 1 by 2 minus 1 by 1. Now you can take, you have to solve this equation, this part of equation. Take LCM, and its LCM is 2, 2, 1, 1 is 1 minus 1 to 2 and 2, and answer will be minus 1 over 2. So just minus 1 over 2 will be multiplied with this z square over 4 pi epsilon r, and minus will be here, and 2 will be multiplied with 4. You got z square over 8 pi epsilon r, and here this is the r is the radius. So you must remember the equation for calculating of the radius, that is n square h square epsilon divided z pi m e square. So putting the value of r here in this way, like this, n square h square epsilon, and then solving this. How you will solve? Keep this factor, take this factor on the above numerator and keep this here like this one. En equals to ze square 8 pi epsilon. This is the previous value. So this n square h square e epsilon will be keep here, will be kept n2 h2 epsilon, and these factors z pi, only this one denominator, we will take it to the upward in the numerator, z pi m e square. So you can cancel the common factors and add r, z square, this z and z, e square e raised power 4 m epsilon epsilon in this way, like m, this is this m, z, these are both z, e raised power 4 this e square 8, this one epsilon, and this epsilon square, n square and h square. So you got this equation for the energy of the nth orbit in any orbit. And if you are using this for hydrogen, and you know hydrogen's atomic number is 1, but if you are using for helium, then its atomic number is 2. If you are using for lithium, its atomic number will be 3. And while n can be any orbit, first, second, third, fourth, and all other these that is in the circle, these are constant. So this equation, we got this equation for hydrogen atom, this one. So this equation will be like m e raised power 4 a epsilon square n square h square. Keep the these constant out and variable on one side, like this, and putting all the values of the constant, you got this minus 2.18 10 raised power minus 18. This is the joule, and you can also represent this with k factor, like this. K is also this the combination of constants, and it has a value 2.18 10 raised power minus 18. So you can write k here divided by n square, and this value is in joule. If you want to convert this value into kilojoule, for kilo you have to divide by 1000, and for per mole you have to multiply with Avogadro's number. Then this value converted into kilojoule per mole, and it has a numerical value of 1313.35 kilojoule per mole. So finally you can use this equation to calculate the energy of any orbit, any energy shell, any energy level, any shell, like E1 for 1 n square, 1 square is 1, answer will be same. For E2 2 square, so this will be divided by 4 and you got this answer. Similarly you can calculate for energy level 3, E3 for 4, 5 and so on. And the lowest energy level, that is the E1 in this case, this is called the ground state energy level, and while others all will be called excited state, like E2, E3, 4, E5, excited state energy levels. And you can find the difference of this, like E2 minus E1, like this one, we got 985 kilojoule per. Even you can calculate the difference E3 minus E2 by their difference. Even you can calculate the difference E4 minus E3, and even you can predict either these difference of energy is increasing or decreasing. This is the question for you. Find the difference and find out their order, either their energy gaps are increasing or decreasing. So one, we can calculate the difference of energy in this way by this equation. Even you can have a direct equation like this: delta equals to E2 minus E1, and E1 is always for lower orbit and E2 is always for higher orbit. And this is the energy, just this one. Only for n orbit you have to keep the 2, and for 1 you have to put the value 1. 1 multiplied by 1, that gives you plus this one. Now thus rearrange above equation. Take this equation side there and this in this way. This one, n1 square here, and this with minus this n2 square. And now keep the common factors out of the brackets. These are common. mg square is raised power 4 8 epsilon 2 is square, h square, are 1 over n1 square minus 1 over n2 square. And if you are using for hydrogen, this will be factor 1. So keeping the common factors out, and you can say for hydrogen atom you have to keep the atomic number 1, and now you got equation in this way. And this is a combination of constant, and here this will be represented by k, and putting the values we got the numerical value, that is 2.18 10 per minus 18 joule. And like this one, n1 again I told you for lower energy level, and n2, like suppose we want to calculate for E1 and E2. For E1 n will be 1, for E2 n will be 2. So n square and 1 square, and solving this part of equation and then multiplying with this value, you got the 1.635 10 per minus 18 joule. Remember, this is in joule. If you want to convert this into kilojoule per mole, then you have to multiply with Avogadro's number and dividing by 1000. This will convert into kilojoule per mole, and in kilojoule it is 985 kilojoule per mole. Students, if you remember, this is the same numerical value as we calculated in previous slides for difference of energy, that E2 minus E1. Like this, you can see here, this one 985 from E2 minus E1. So you can calculate the difference of energy using that energy formulas, and you can also use by using direct this equation. Now is the derivation of frequency. Frequency nu, this is represented by nu, and according to Planck's theory, delta E is equal to h nu. Here h is Planck's constant, and its value is 6.62 10 raised per minus 34 joule second. And this one, just we have calculated the difference in energy. This is the delta E. Keeping this, putting the value of delta E and comparing it with h nu. H is Planck's constant. Divide this h by this, like h2, and now frequency, this one. So you can calculate these all are constant. For hydrogen, atomic number 1, for lithium atomic number 3, for helium atomic number 2, and n1 again I am telling you this is for lower energy orbit, and n2 is for higher energy orbit. So in this way you can calculate the frequency. Similarly, the wave number, relationship between frequency nu and wave number is nu bar, is nu equals to nu bar c. C is the velocity of light, and you know its value is 3 into 10 raised power meter per second. 3 into 10 raised power 8 meter per second. So this is the equation like this. This one is for frequency nu, and C, dividing C here like this, you can find the nu bar, and this for this one, because atomic number for hydrogen is 1, helium is 2. Other than this, m e raised power 4 divided by 8 epsilon square h cube c. This is called Rydberg constant, this one. And in the exam you can be asked as what is Rydberg constant. So you must know that this combination of constant, also its value. This is represented by capital R, Rydberg constant. You can write this R. So again, N1 stands for lower energy level or lower orbit, and N2 stands for higher energy level or higher orbit. So you can calculate using this equation the nu bar or the wave number. These are the practice questions. These are just simple examples. You have to use the different expressions and putting the values of constants. You can calculate the you can solve the examples. These are very easy, just to practice it. Here are the some short response question, and this was the objective of our today's lecture. Relationship between energy wavelength and frequency and wavelength. That is very easy. And energy is equal to hc over lambda. You know already know the value of E. If Planck's constant, C is the velocity of light, and the lambda is the wavelength. So keeping the wavelength on one side and taking all the values other side, just put the values of constant, h that is Planck's constant, c velocity of light, and E is the energy of the nth orbit. You can calculate the energy, and even you can wavelength. And even you can calculate the wavelength from the frequency by using this equation. Nu is equal to C over lambda. Frequency we have just calculated, divided, and you know the C, velocity of light, you can calculate the wavelength. Calculate the energy of the hydrogen atom in the orbit of, for which the value of n is 3, means orbit number is 3. So apply the formula to calculate the energy, and there keep the n value of n 3. So E3 you have to calculate with minus 1313.35 divided by 3 square. I have already calculated in these slides in this lecture. Okay, question is for you. Do you think Bohr's model is applicable to all types of atoms? No, this is applicable to monoelectron system like hydrogen, helium ion, and lithium ion. So today's students, we have learned about the applications of the Bohr's model, and we have calculated the energy, frequency, wave number, and next topic is also about Niels Bohr's atomic model, but this is the limitations of Bohr's atomic model, or you can say the defects of the Bohr's atomic model.